we are very lucky to have a bunch of very, very distinguished speakers, but in order to focus on the science, I'm going to keep the introduction to a minimum in the main sessions. They are all very distinguished nonetheless. So Daniel Su from Columbia University is going to tell us about predictive models from interpolation.
Okay, thanks, Sebastian. Thanks for the invitation. This is a great workshop. I want to tell you about predictive models from interpolation. And so a lot of the introduction to my talk, it's already been covered by Peter, but I'll just run through it a little bit. So maybe this is not a surprise anymore, but maybe a few years ago, maybe we might have thought that, when you open up a textbook that, overfitting to the training data might be considered something that would lead to bad predictive performance out of sample. And this was certainly the case for, that people had been, buying into this conventional wisdom. And it's really been sort of deep learning empiricists who have really raised this question again in the past several years, whether this is actually the right intuition to have. And we're going to give some empirical and theoretical evidence that goes against this conventional wisdom, at least for the types of scenarios that are coming up in practice these days. Okay, so here's an outline of the talk. I will describe some of these empirical observations that Peter already kind of touched upon. And this will motivate us to look at some certain kinds of interpolating rules for supervised learning. One based on local prediction, because these are ones that we understand well. And of course, we would like to eventually understand interpolating rules based on neural networks. Okay, just so we're all on the same page, we're talking about supervised learning. So supervised learning is when you have training examples. Typically, we assume that they're IID from some distribution. And these get passed through a learning algorithm that produces some prediction rule, a prediction function, on which we want to classify or make a prediction about a new test point. And we measure whether our prediction is accurate based on some loss function, and we care about what happens in the average case sense. So what has happened in the past several years with people studying deep nets, but also other kinds of sort of large predictive models, is that they are finding that these sort of large models can interpolate any training data. That's perhaps not surprising at all. But what's sort of interesting is that they also generalize well. In other words, they have good out-of-sample prediction performance, even when you're perfectly fitting noisy training data. Okay. So here's a plot from a paper by Belkin, Ma, and Mandel, where they add noise to some supervised training data. And you add just by randomly flipping some of the labels. And you would expect that if you look at the test error at the end of the day, that it does increase as the amount of noise that you add, but it doesn't immediately shoot from 0 to the trivial noise rate, which is 90% in this case, which is this is a 10-class problem. I think it's MNIST. But instead, it kind of stays not too far from what the Bayes optimal classification error rate is for these various kinds of models. So this is 2 different kernel machines, and as well as a 2-layer fully connected neural network. Okay. So the test risk is maybe what you would expect from the Bayes risk plus some small amount. Okay, so maybe this is not totally surprising. Because we have seen large predictive models work well out of sample, but this is maybe surprising in the context, at least for regression, where we are literally fitting the noise in the training data, and yet we have good predictive performance. So at least in the context of classification, people kind of had a good understanding of what was going on, and certainly people studying nonparametric methods and statistics knew that it's not necessarily a bad thing to have very large models or many parameters. And indeed, some statisticians were looking at some different class of very large predictive models. These are boosted decision trees, where they were able to interpret these things, at least empirically, as some kind of local interpolation methods. And they argued that the locality of these prediction rules, the flexibility of these prediction rules, is what gives these models the predictive power. In other words, that they are very robust to label noise. So here they're trying to illustrate this phenomenon where if you have a less flexible prediction rule like a linear classifier and there's some label noise, you would have to drastically sort of change the prediction rule to deal with a particular label being noisy, whereas a more flexible prediction rule would be able to accommodate that noisy label much more gracefully. Okay. So this gives us some inspiration to look at local prediction rules for why it is the case that we can actually do interpolation and still expect good out-of-sample prediction performance. So before our work, we knew of two local interpolation methods that had been sort of studied and analyzed in the literature. One is super well known, which is nearest neighbor. So everyone knows this. If you take machine learning 101, you know that this is a classifier or a prediction rule that perfectly interpolates the training data, assuming that you don't have replicating any data points with conflicting labels. And we, in some sense, really understand its properties. Its prediction error sort of converges asymptotically to something like twice the Bayes optimal risk. And another method that's also slightly less well known, but is surprisingly has very surprisingly strong theoretical guarantee, is this smoothing kernel method called the Hilbert kernel. I think outside of statistics is called the Shepard's method. This also turns out to interpolate training data, and it has some kind of consistency property. As long as your data has a density, you can show some kind of consistency. As n goes to infinity, the risk approaches the Bayes optimal. So there's some things that are not nice about it. For instance, there aren't convergence rates, and there's other deficiencies about this rule. Okay. But this at least gives us some hope that this is the plausible explanation for why it is that we can construct prediction rules that interpolate training data and yet give good out-of-sample performance. Okay. So the goals of this line of work is to first try to counter this conventional wisdom that perfectly fitting training data necessarily leads to bad predictive performance. Okay? So we can show that there are some interpolation methods that are consistent, or in a sense that I'll describe later, almost consistent for both classification and regression. And I'll describe two of them that are based on local interpolation, and then I'll try to say something about neural nets, but given some caveats, they're really about linear models. But throughout this, we'd like to try to identify what are the useful properties of these methods that make the interpolation benign or give good out-of-sample performance. Okay, and of course, we ultimately like to make connections to practical methods. Okay, so this will be so I'll kind of go through these three methods depending on how much time I have. So let's start with the two local prediction rules. Okay, so the name of the game here is to try to estimate the regression function. So the regression function is the function that has the smallest mean squared error out of sample. It's just a conditional expectation of the label given the input x. And these local prediction rules try to construct some estimate of this function. And if you were to use this for binary classification, let's say the labels are just 0 or 1, then this is just the conditional probability that the label is 1 given the input. Okay, and the optimal classifier is just by thresholding at a half, and you can construct the classifier just by thresholding your estimate eta hat at a half as well. Okay. And so what do we mean by good predictive performance? We care about what happens with the out-of-sample prediction, because in sample, everything is your training error or training loss is only 0 because you're interpolating the training data. So we care about what happens out of sample. Well, we also care about what happens out of sample, let's say as you collect more and more data, as n goes to infinity, and how quickly it approaches whatever it converges to. Okay. So let me describe the first method that we constructed for this, which is simplicial interpolation. Peter mentioned this in his talk. So in this method, the basic idea is to construct some kind of multivariate triangulation of your training data just based on the x parts. So let's say that your x's come from, okay, I didn't say it here, but so x's are d-dimensional vectors, and the y's are labels between 0 and 1. For classification, it would be 0 or 1. And so the way this interpolation works is that you construct some triangulation of your training examples, x1 through xn, of the convex hull of your training examples, for instance, using Delaunay triangulation. Okay, this is just if you just look at the Voronoi diagram that associated with nearest neighbor, this is the dual of that in some sense. And then our prediction rule will be to, on a new point x, it's first locate which triangle or simplex in d dimensions contains that point x, and then to do a linear interpolation of the vertices of that simplex. So the vertices of the simplex will be actual training examples. There'll be d plus 1 of them. And if you do a linear or affine interpolation of their corresponding labels, your prediction rule will go through will perfectly fit the labels of the training examples, but for any other point inside the simplex, it'll be some linear combination of the labels of the training labels. Okay. So the resulting function that you construct is some piecewise linear function on the convex hull of your training examples. Okay. So it kind of looks like this, that the black points here are your training examples. I think the purple lines here show the Voronoi diagram, and the black lines show you the faces of the simplices in this triangulation. Okay. So all the action basically happens on one of the, when you locate which simplex your prediction point, your test point lands in, or I should say, okay, so when you want to do, as I said before, if you're doing classification, you just threshold your regression estimate at a half. Okay. So all the action to analyze this method happen. You just need to consider what happened on a single simplex. So let's look at one simplex, let's say with vertices x1 through xd. Okay, and let's say that the corresponding labels in your training data are y1 through yd, or d plus 1. And let's say that your test point is right here. So you need to make a prediction there. What we'll do is just do a linear or affine interpolation of the labels of x1 through xd plus 1. And so this point here, the way that happens is that this point here has some sort of barycentric coordinates in terms of in this simplex. So x can be written as some convex combination of x1, x2 up to xd plus 1. And then our linear interpolation will be exactly the same weights to use to combine the labels of x1 through xd plus 1. So that will be our estimate or our prediction for the label at x here. And so you can kind of see what is happening here, which is that when you're making this prediction, you are aggregating information from the labels of d plus 1 data points. Okay? And this is in contrast to, say, the one nearest neighbor rule, which is just take the label of just the closest training example. It just doesn't aggregate any information. So already we see a difference with the nearest neighbor rule, and we can make this kind of illustrate this much more dramatically in a very simple case. So here's a particular setup. So let's suppose that in this simplex that I've drawn here, the true labels, the regression function for all the points in that simplex, the regression function is less than a half. Okay, so the probability of a label 1 is less than a half. So the right thing to do there is to always predict 0. Okay, that would be give you the smallest probability of classification error. But suppose on your training data you had noise. So this is so you're going to fit this noise, and most of the points don't have noise, but one of them does. Okay, so noise here means that the label is 1, even though the probability of a label being 1 is less than a half. Now we can look at in this particular simplex what happens with the prediction rule that you construct based on nearest neighbor and based on simplicial interpolation. So based on nearest neighbor, how do you make a prediction? You look at the point and you look at what's the closest point to it. Maybe it's x1, x2, or x3. Well, this is the region in which x3 is the nearest neighbor, and you would go with the prediction of you would predict with the label of x3 in this case, which would be a 1, and that's goes against what the optimal classifier would predict. Whereas in simplicial interpolation, you do a linear interpolation. You take into account the labels of x1 and x2, and so on, as well. And this sort of reduces the region in which you are actually going to make a classification mistake. And you can kind of visually see that there's a difference in, in the size of the regions here, and this is something that will get magnified in high dimensions. Okay, so this is the intuition for why this, these kinds of averaging rules in high dimensions can give you some improvement over what happens with more simplistic rule.
Complexity of this classifier, can you actually compute it quickly?
Yeah. So the way so Ilya is asking a good question. Is this something that you can actually implement? It turns out yes. So just like Voronoi diagram is it's from some kind of large object, so is the case with the triangulation. But we don't actually need to construct the triangulation explicitly. So in nearest neighbor, you don't actually have to construct a Voronoi diagram. You just need an algorithm to make the prediction. The same thing can happen with simplicial interpolation. You just need to locate the simplex that contains your test point, and this can be done by solving a linear program.
So your results are for Delaunay triangulations, or like what types of triangulations?
So the main thing that needs to happen is that the triangles or simplices cannot be too elongated. And so doing a Delaunay triangulation ensures something about that. Yeah, there certainly would be some triangulations that would not have a nice property here.
Related to that question, but in higher dimensions, even Delaunay will produce a lot more skinny triangles. I mean, this is something that is probably fundamentally an issue with simplicial interpolation.
So we can at least can always control sort of the aspect ratio in any dimension, just based on the idea that it's the dual of the Voronoi diagram. Yeah. So at least this theorem will be for Delaunay triangulation, but any triangulation that can control this aspect ratio. So this theorem is about the asymptotic risk of this particular prediction rule. So let's just look at it for classification, because that's the kind of scenario that I described before. So there's some pretty strong assumptions on the data distribution, but it sort of illustrates the point that I want to make here. So the data distribution should be uniform with some convex set, and the regression function should be always bounded away from a half. Okay, so this is like an easy classification problem where there's some sort of effectively some kind of margin. So what happened? So we know exactly what would happen for nearest neighbor. It would still converge to something kind of like twice the base risk. But in this case, with simplicial interpolation, the risk, the expected 0-1 loss, converges to something that's bounded by, something closer to 1. Okay, what is it closer to 1 times the base risk? Well, it's 1 plus something that's exponentially small in the dimension. And this is sort of to be expected, because you are now being able to aggregate information from not just one, your prediction not just based on one data point, but on d plus 1 data points. Okay. Right, so the comparison point here is nearest neighbor. Asymptotically, it converges to something kind of like twice the base risk. Okay. And we say something also about regression. For regression error, it's sort of like 1 plus something that gets smaller in higher dimensions. Okay, so we already see some benefit of high dimensions and averaging, and the same thing can be done with a different interpolation scheme, which is based on sort of an analog of k nearest neighbor. So regular k nearest neighbor is not interpolating because you are doing some averaging or voting over your k nearest neighbors. But if you do some weighted averaging, you can make it interpolating. So Peter mentioned that you can use the idea that you can use some kind of singular kernel or singular weighting scheme, and so we can do the same thing here. So let's say you want to make a prediction at x. You could look at the k nearest neighbor and then look at its corresponding labels. And if you just did a vote or an average, you would not be interpolating the training data, but you can sort of combine them in some weighted fashion so that you are interpolating. So this is a particular weighting scheme that depends inversely on the distance to the test point. So if x is right on top of one of the the training points, the weight would be infinity, and so all of your weight would be. And you're doing some normalization here, so we just predict the label of that corresponding training point, and away from any of the training data, it does some averaging. Okay. So this indeed does give you some kind of interpolation. This was actually known, so as I mentioned, this is a scheme like this where you don't just restrict to the k nearest neighbor, but you look at this thing over all of your training data, this is something called the Hilbert kernel estimate. That was studied in the literature before. But I mentioned this is consistent, but didn't have any non-asymptotic rates. Whereas if you just localize to just the k-nearest neighbor, you do get optimal non-parametric rates. It seems like the localization is essential in this case. So the theorem that we can prove about this scheme is sort of a kind of a theorem that you would expect for non-parametric regression. So again, we have some strong assumptions about on x prime, on the distribution of x's. There's some regularity conditions I don't want to get into. And if we look at what happens when the regression function is smooth, then the expected mean squared error is something that goes to 0 with n at the rate that's minimax optimal. Okay. So there's no sort of, at least in terms of minimax rates, there's not a cost to doing interpolation. This is something that was pointed out in a follow-up work by Misha, Sasha, and Sasha for a different non-parametric method that also uses some localization because it's a singular kernel, but it's a compact kernel. So it's sort of supported on a compact set. Okay. So localization seemed to be important in that case as well. So we've seen two schemes where you use some kind of localization for your prediction, and somehow in this case, even if you are interpolating, the effect of the noise does not hurt much the predictive out-of-sample prediction accuracy of your prediction rule. Okay, so this was about two schemes that. Okay, so I guess people do use nearest neighbor, and I guess some people use these kinds of non-parametric regressions. But okay, so this is supposed to be about neural nets, so we should talk about the other kind of NN, which is neural nets. So what can we say about neural nets? So really not a whole lot, but we can done some experiments to show that sort of things do maybe are not as exactly what you might expect. So this is a case where we are fitting just two-layer neural nets with one hidden layer. In the first case, we don't train the first layer. In the second case, we are training the first layer. And these are just on MNIST problems, so really simple data sets. And this is the test risk. The training risk always goes to 0. Not always, but pretty close to 0. But the test risk kind of shows these two behaviors. So when you have a very narrow network, in other words, the number of hidden units is very small, then you are sort of in the parametric regime. You are basically implementing something like some parametric model, and there seems to be some trade-off in terms of bias and variance. But once you go beyond that, when you are actually interpolating the training data, this is some point when you have enough hidden units so that becomes possible, we are sort of in a more interesting regime. Okay, and that's given by the second descent here. Okay, so this is something that we drew a cartoon about and called it double descent, but really the interesting part is what's going on this right part beyond the point where you are perfectly fitting the training data. Okay. Somehow, I think the x-axis of this plot is a little bit artificial. It's sort of, why do we care about the number of hidden units? Is this maybe just something for computers? It's nice to have small number of hidden units. Maybe it's good for people, but maybe nature does not really care about how many hidden units you really have. Okay, so what really matters is something else, which is the inductive bias. Okay. And people have looked at what happens on the right-hand side of this curve in other contexts, particularly for classification. And the story for classification has been that, okay, what's happening when you have higher and higher capacity is that maybe you can achieve higher and higher margins on your training data. Okay. And so the hope is that we can have an analogous story for regression, and that's starting to emerge. Okay. So here's one possible explanation for what's going on in the right-hand side. Is that when you increase the number of hidden units, you are better approximating some kind of kernel, and this would be exactly the case if you are doing this random Fourier features, which is the case in this experiment. So here you do not train the first layer of weights, but you only train the second layer. then we know as you increase the number of hidden units, this is getting closer and closer to approximating a certain kernel machine. And what happens, at least in the experiments, is that we can see the test risk is going down as we increase the number of hidden units, but so is the norm, the RKHS norm of your solution. Okay? So it seems like in this case, for this particular problem, this is a speech data set, having small RKHS norm is the right inductive bias for the problem, and you're better able to align yourself with this inductive bias by having more and more hidden units. So that's really the only thing that can help you here, because in this case, every point to the right of this threshold here, the training risk is 0. So there's nothing about the training data or the fit to the data that can help you. Everything is determined by your inductive bias. So whether or not the inductive bias is right with your method, that will ultimately determine how good your predictive model is. So we don't have any theory about this, but I guess Andrea will tell us about some theory about what happens here. We can again show you something in the linear regression setting for why it is the case that, is it ever the case that you have a smaller risk when you have more features than when you try to do some balancing of bias and variance. So we study this in the context of Gaussian linear regression, this kind of same setup as Peter, but we have a slightly different setup. But our main question is not just about what is the asymptotic risk or the non-asymptotic risk of the right endpoint here, but we want to know, is there a particular point along this x-axis that we should really be thinking about? Okay. Is it ever the case that we want to be to the left of the interpolation threshold or to the right? Okay. So here we have to look at a particular fixed problem and then ask how many features should we be using in this linear regression model. And we can show under some kind of eigenvalue conditions, this is, of course, has to determine how well, this of course, as Peter showed, that determines what happens at the right endpoint. But under some other assumptions, we can actually show that there's nothing to the left of the interpolating threshold that has a smaller risk than the right endpoint there. Okay. So this is a setting where we can show that there are cases where, there's a benefit to doing interpolation as long as you are sort of choosing an interpolator that sort of aligns well with the right inductive bias. So I think this, I want to sum up here. I think, by now, I think over the past year or so, it's becoming more and more clear that interpolation, overfitting, it's not really the same way that we should, we should not think about it the same way that we think about overfitting and interpolation for parametric models, or at least very small capacity models. Somehow the behavior is very different when you are looking at overparameterized or somehow very large predictive models. And of course, in these cases, everything is about the inductive bias, because the data fitting is not providing you any way to distinguish between different interpolating models. So we identified 2 different properties of what might be good interpolators. The first was the local prediction method. Smoothness from some kind of averaging in high dimensions seems to be one property that can be beneficial. And then for things like neural nets or kernel machines, at least with linear models, some kind of low function space norm seems to be important as well. So I think the main open problems with interpolation is to try to understand what is the inductive bias for other predictive models or learning algorithms that we use in practice. And we have some ideas about what training neural nets with gradient descent does, but I don't think this is fully answered yet. And really, again, like Peter, I'm not advocating that we find interpolating fits. This is just a phenomenon that we want to understand. But maybe there are benefits to doing interpolation. So we have some stylized scenarios where we can say that there are, but maybe the question is whether this actually comes out in practice. Thanks.
Okay, we have time for questions and comments. Adi?
So I was confused by the double descent curve. After the training error has gone to 0, if I'm using batch gradient descent, I shouldn't be having any gradient at that point, right? So is it like you're using stochastic gradient descent to do the interpolation threshold?
in this particular experiment, yeah, we didn't quite make it all the way to 0 here, but in like a simpler problem where the optimization is easy, we can't make it actually 0.
Actually, I have a question on the last theorem that you showed, and there's a picture next to it. Do you prove that this picture is what happens, or it's just?
Yeah. Okay. So not the full curve, but we can.
Okay. Yeah. That's what.
Not the full everything, but we can. Okay. So I mean, I guess this is easy to prove, but.
I guess you can show 3 points, like there's a high, a low, a high, and then a very low.
Yeah. I mean, this one is kind of also trivial, but the question is whether this part here is lower or higher than this point here, and that's something that's interesting to ask. And that's what we can say something about.
But, okay. Cool. Thanks again.
Thanks.
Okay, so next we have Sasha Rakhlin from MIT, who is going to tell us about learning methods that memorize data.
Okay, thanks. Thanks for the invitation to this nice workshop. So I will continue the line of talks with Peter and Daniel, and luckily I can spend less time now on introductions. So let me just say that this is based on work with, so the first paper with Misha Belkin and Sasha Tsibakov. I'll just briefly mention this in light of Daniel's talk. And then there's work with Tengyuan Liang at U Chicago and my current student Shiyu Zhai. So the question we would like to understand is, can a learning method be successful if it memorizes the training data? Okay, there are 2 talks now on this subject. So this is the outline of my talk. I will first very briefly describe the Nadaraya-Watson estimator. Daniel already described a version of that result. And then I will talk about kernel ridgeless regression. And I will present 3 results. First one is when the dimension is constant, so it's not a high-dimensional problem. The second regime is when dimensionality is n to some alpha, when alpha is between 0 and 1. And the third result that I will present is in the regime of dimension of the data being on the order of number of data points. Okay, and then I will sketch the application to wide neural networks in the final part. Okay, so again, you take let's say MNIST data set, you take 2 digits, treat it as a regression problem, and do kernel ridge regression with some lambda. And what you see in terms of out-of-sample performance of this estimator is that as you decrease lambda all the way to 0, you get better and better out-of-sample. So it only helps to fit the data better and better. And so the question is why this is happening, and we would like to understand. Again, we're not advocating this necessarily as a solution, but just to understand what are the generalization properties of such a interpolating method. And so we're motivated by, in particular, by this paper that Misha and Sion and Somik wrote, arguing that to understand deep learning, we need to first understand kernel learning. And our path through this has been to start with these local methods such as Nadaraya-Watson estimator and the type of methods that Daniel just spoke about. Then talk about more global kernel methods such as the minimal norm interpolation of the data, and then say something about neural networks. Okay, so this has been our kind of path through these topics. Okay, so very briefly, let me just spend 5 minutes or less on this. The Nadaraya-Watson estimator, the data is pairs yi equal to f star of xi plus noise. So this is the classical well-specified case. And you know that f star is smooth. The classical Nadaraya-Watson estimator from the 60s at least is to average the y values according to some measure of the distance between the point of interest x and all of your data points, and average the y values for those data points. And this weighting is done according to a kernel function. which is appropriately scaled by h, which is the bandwidth of this kernel. Okay, so the types of kernel you can consider are like a box kernel, or 1 minus x squared positive part, or this Gaussian style kernel, and so forth. So what's important is that you can put a box of a kind of a constant area under this curve, so that there is some averaging that's happening locally. And all of those will work with the results that I will discuss. Okay, so for this classical method, what controls fit to data? Well, it's clear that fit to data is actually controlled by the height of the kernel at 0. Okay, and that you can just read off from this formula. If the height of the kernel is very high at 0, then you're preferring points which are very near, much more than the rest. And so in this averaging, only the point where you're querying at the data point that you've seen survives. And so in particular, if you define a kernel, for instance, as 1 over the norm to the power a, and then min with some cap tau, then you see that as you increase tau to infinity, you get better and better interpolating solutions. Okay, and the point is that this has nothing to do with the actual bias variance trade-off that's happening when you work with these estimators. So the fit to data has nothing to do with the choice of the cap at 0. Okay, and so as Daniel mentioned, this the kernel of this sort has been analyzed by Devroy et al. In '98, and it was shown to be consistent. What is interesting is that it's a wild kernel, and it converges nowhere. So if you fix a point, then you don't have convergence at this point as n goes to infinity. So there will be an infinitely long sequence of points where times where this just doesn't behave well. Okay, so what the difficulty, as Daniel mentioned, what happens here is that this kernel is too global, and you can't put a bandwidth into this kernel because it will just cancel in that numerator and denominator calculation, and so you cannot control the bias. And so what we did in our work, and this is similar to the work follow-up to Daniel work with Misha and Mitra, is that we cap the kernel at some radius 1, and then show that you can still choose a bandwidth for this kernel in the minimax optimal way. That gives you a minimax optimal rate for any dimension d, assuming that the underlying regression function is beta Hölder. And f hat n is interpolating if you set that tau to go to infinity. So the takeaway, and this is a very quick summary of this result, this is not a surprising result, but it just says that fit to data has nothing to do with the bias variance trade-off necessarily, right? So you can come up with situations where there is bias variance trade-off, but it's not reflected in the values on the training data. Okay. And in particular, this height of the kernel, as parameterized by tau, height of the kernel at 0, is completely decoupled from the bias variance trade-off, which is given by the bandwidth parameter h. Okay, so that's a very simple result that says that there is a bit more to this story. And of course, by the way, when you see this, it becomes obvious that you can take any estimator and just put little bumps on your favorite estimator to fit the data. That's obvious. You will not see any change in terms of the L2 out of sample performance, but it will be interpolating the data. Okay, so the point of this is just to see whether current existing standard classical methods, in fact, have this interplay of fit to data and bias variance trade-off, and you can see that you can decouple these. All right. So there is more to this picture, as Daniel already discussed, and as Peter discussed, in the sense that the point where that the fit to training data is low can occur anywhere on this regimes, anywhere on this plot, and it's not necessarily that you have this shape of the bias variance. You can have more complicated shapes, but importantly, the behavior on training data doesn't really tell you where you are. I think that's a key thing to kind of take away. Right? You cannot deduce from performance on training sample where you are in this picture. Okay, so let me talk about something that's more interesting, which is kernel ridgeless regression or minimal norm interpolation. I will use these two terms interchangeably. And let me define this method first. So we're probably familiar with kernel ridge regression. It's just square fit to data penalized by some norm in a reproducing kernel Hilbert space. And the usual conventional wisdom is that you need to have a non-zero regularizer if this Hilbert space is infinite dimensional or high dimensional. And there is a classical line of work which tells you how to choose that regularization parameter, at least in theory, to obtain the correct behavior. But in practice, as I already mentioned in the beginning, interpolated solutions, which is when you set lambda to be equal to 0, perform quite well in practice. And so we would like to understand this phenomenon. Of course, when you set lambda to 0, there are infinitely many solutions. And so what we do is we pick the minimal norm solution that interpolates the data, so that you can think of this as the limit of the previous definition as lambda goes to 0. A couple of remarks. So first, we still are enforcing simplicity, right? So if you think of the classical machine learning Occam razor, we are choosing a simple solution. But the simplicity is not reflected on you don't suffer in terms of the fit to data, right? So previously, when you regularize, you pull away from the data points. But here, we're saying, just suppose that you go through the data points and still choose a simple solution, right? That's the bottom line, right? So it is conceivable that such a minimal norm interpolant generalizes. It's not out of the question. We're still not choosing completely crazy solutions. And also, there is this line of work that connects to gradient descent and stochastic gradient descent that you converge to this solution if you start from 0 and you do gradient descent. And also, there's a line of work on neural tangent kernels that show that neural networks, if they're sufficiently wide and they're initialized appropriately, randomly, then they converge to a ridgeless regression solution. So I'm using ridgeless regression and minimal norm interpolation interchangeably, same thing. Okay? So let's think about the regime where dimension is constant. This is the input dimension of the data, x. So x is in RD. And the result that Peter mentioned is, for this particular kernel, although I don't think this is too special, this is chosen for convenience, take a Laplace kernel, defined in this way, that's a Euclidean norm on the input space x, and sigma is the width of this kernel, right? So this is how wide that Laplace kernel is. And let's do minimal norm interpolation with respect to this kernel. So the theorem, this is work with Shiyu Zhai, is that for odd dimension D, for technical reasons, it's for odd dimensions, but I don't think there is anything special. With that probability, no matter how you choose the bandwidth of the kernel, it will not be consistent. So risk is lower bounded by a constant as long as D is constant. So if you think of D as being constant, with respect to N, you do not have consistency unless you make some further strong assumptions. Okay. So the result that I described before on the Nadaraya-Watson kernel, that and the one that Daniel described, that works in any dimension. And that's a local method. This is a global method. It takes the data, your data set, and then instead of just locally averaging, it does something, it solves an inverse problem. And this result shows that you really cannot get consistency in low dimension. It has to be a high dimensional phenomenon if it even exists. Okay. So just one word about the proof. Imagine that you take the bandwidth to be too large, then the solution that you get, this minimal norm interpolant, at least in one dimension, you can think of this as a rope hanging between nails, right? So that's exactly the solution of a rope hanging from nails in one dimension. And so as you tighten sigma, you get either a linear interpolant. I should ask physicists, is that true? As you tighten sigma, you get a piecewise linear interpolation, which is related to what Daniel talked about. And that clearly is not going to be consistent. And if you put sigma to be too low, then it will just hang all the way to the ground, right? So these are the two regimes. So this is the regime where you fit the noisy value of the function, but you're not able to come back to this function quickly enough. So you suffer in terms of the prediction performance here around xi. And the other regime is that it's just hanging all the way to the ground, and then you're off here. And what the result shows is that these two regimes cover all the choices for sigma. So there's no way, even after looking at data, there's no way you can choose sigma in a way that it will make it work. Okay, so that's the only kind of that's not only, but that's a surprising kind of thing about this result, is that there is no way to adaptively choose the bandwidth. You're just doomed. Okay, so if kernel rigidless regression, if this minimal norm interpolation works, it has to be a high dimensional phenomenon, or you have more assumptions on the data somehow. Okay, so now let me talk about this result, which should appear, or should be pushed to archive maybe tonight. There is no happy hour, right, tonight? Or is there? There is a happy hour? Okay, tomorrow. There is no happy hour tomorrow, right? No, okay, so tomorrow. So this is a regime d to the, proportional to n to the alpha between 0 and 1. And so we're thinking of n being large, but also dimensionality being large. So dimension grows, if you wish, with n. This is the result that we get, and I should mention that this is an upper bound on risk, and we do not know if this phenomenon is real or not, and we should ask some physicists sitting in the room whether it is. So what we get is the following multiple descent shape, at least for the upper bound on the risk. So on the x-axis, we have a parameterization of the problem in terms of how d scales with n. So here d is n to the alpha. Alpha goes from 0 to 1. And this is the rate for the risk for out-of-sampler performance of minimal norm interpolation. And it has this interesting behavior that at integer powers of 1 over alpha, at integer powers it gets better. And then, for reasons that you will see in a second, this upper bound becomes vacuous at integer powers and then dips again and again and again. And so you have this multiple, instead of double descent, as Daniel was describing, it has a multiple descent behavior. So we don't know if it's real. We tried to get a lower bound, and someone maybe here has more tools to prove a lower bound.
So here, what is the assumption on the function?
The function, I will state it in a second. I will state the assumptions. Here are the assumptions. Okay, so what we look at is a kernel of the form inner product. So it's some function of inner product, A. So H is the function of the inner product. We assume that x's are IID in d dimensions. And for simplicity, we assume that all the coordinates are IID as well. Okay. One can try to relax that, but because we're discussing a high-dimensional phenomenon, we need some independence in the coordinates, as Peter was mentioning. We assume that we have a Taylor expansion that converges everywhere, and that the coefficients of this Taylor expansion are positive. Okay, so for that reason, we need to modify slightly this neural network result to add a bias so that we have all the coefficients being positive. That's in the later part. We assume that the regression function y given x lives in RKHS. This should be small k. It doesn't matter. And it can be written in this form with a bounded rho star. Okay, that's our assumption. Right. Any questions about this? Okay. So here is the result that we obtained. In this scaling, d is n to the alpha. For alpha between 1 over integer k0 plus 1 and 1 over k in these fractional intervals, the out-of-sample performance, or the risk of this estimator, the minimal norm interpolant, is d to the k0 over n plus n over d to the k0 plus 1. So this is really just getting anything out of this minimal norm interpolation. And by the way, we're not using any assumptions about the low rankness of data or anything. This is a full rank story, right? And you see that here, as n goes between these two integer powers, you do get a rate of n to the minus beta with that shape. Okay. So let me give you in the next 2 minutes some intuition. The minimal norm interpolant has this form. That's not difficult to see, where the kx, capital X, is the vector of kernel evaluations between x and x1 up to xn. And kx inverse is this inverse of the kernel matrix of all the pairwise kernel evaluations. So that's the empirical kernel matrix. And now you can write out the bias variance decomposition. This is the variance term, and this is the bias term. The second one is the bias square term. And essentially, I didn't write it down, but in one line you can see that the variance term is this, right? And this is where all the work is, to show that this term can go to 0. And in terms of the bias, we didn't spend too much time on the bias, and just under that assumption that we made here, under this assumption, we show that the variance is the dominant term. So the bias squared is less than variance. So we just focus on this, and you can see that there's quite a work to do. Here, x is a random variable from that distribution, and this is the empirical kernel matrix. So you have to understand spectral properties of these random kernel matrices. And let me give you a roadmap of the proof, just very briefly. So we look at the Taylor expansion of the kernel, and we truncate the Taylor expansion, and we look at the kernel with the truncation up to k. Okay, so this is think of this as another kernel matrix, but the kernel has been truncated. And what we prove, and a lot of heavy lifting here was done by Shiyu Zhai, the student, is that with hyperability for all the k below k0, so remember k0 is that integer, so that alpha falls between 1 over k0 and 1 over k0 plus 1. For all the k up to that level, this matrix k to the k, the truncated matrix, has d plus k over k non-zero eigenvalues, and all of them are larger than d to the minus k. Okay. You have comments?
Yeah, so okay, perhaps a small comment that is, there is this paper that I was mentioning to you during the break. And so there we prove a lower bound that is also a lower bound for kernel ridge regression. And you know, the technique looks very similar. The setting is slightly different, it's on the sphere, but I think we have basically a similar lower bound on the eigenvalues of the kernel matrix.
In the same regime. Okay. You assume Gaussian input, or?
We assume input uniform on the sphere in the
I see.
dimension.
Okay. Okay. We do not assume a particular form of the distribution on the coordinate. So we cannot go to Hermite polynomials or some known basis. So what we do is we okay. So you write the kernel matrix in this form where each phi is indexed by the data point I and some choice of the powers on the polynomial. So this P R1 through RD is you put power R1 on the first coordinate, R2 on the second coordinate, and power RD on the dth coordinate. This one is difficult to analyze because of the correlations. We have a we do Grant-Schmidt orthogonalization on this basis 1 z is squared and so forth with respect to L2p, and pass to a different representation, and then show that this Grant-Schmidt process has a finite operator of lambda is bounded. Okay. So now it's much easier to work with this basis, and what we show is a certain small ball property for these functions. The small ball property, if you've seen kind of analysis of least eigenvalue, then by Shahar Mendelssohn and Vladimir Kolchinsky and others, this type of analysis shows up, and that gives the lower bound on the eigenvalue. Okay, I'm running out of time. Okay, so that's the picture that we get. We don't know if it's real or not, but essentially, as you hit the integer power, you're gaining one more dimension in that expansion, the Taylor expansion, and it takes data to kind of get better in now with that extra dimension, and so that's why you see these strange form, at least in the upper bound, and maybe someone can prove a lower bound.
So just to clarify, for the lower bound, you don't know for any d, for any n to the alpha, like you don't know any alpha for which it's like...
For which it's tight? No, this is just
not even tight, but just, yeah, like the rate is not going to 0.
Alpha equals 1.
Yeah, alpha equals 0 even.
So alpha equals to 0, we know that it cannot be done, and I have 1 minute left, so I can discuss this point. Mm-hmm. Okay, 3 more minutes, good. Okay, so actually maybe I should skip this. So in this regime d equals to n, or proportional to n at this point, this at least doesn't give you anything, but this result doesn't assume anything about the data. And so in the work with Tengyuan Liang, what we did previously is to analyze this point and show that if you do have something about the data, such as a spectral decay of the data, then you can still get something that is small. Okay, so you could get good performance in this regime under the additional assumptions, like in Peter's talk, that the rank or some effective rank of the data is small. Okay. Okay, so that's that. Let me not do the details of this and just briefly say, okay, I think people know this. You take a wide neural network that's randomly initialized with W, each coordinate of W being drawn from, let's say, normal. So again, we have to do this. We have to append this coordinate so that all the coefficients are positive in the Taylor expansion, and then you calculate the gradient of the square loss, and then you see that the gradient flow gives you a convergence of this function on any point. So for all points, this converges to a ridgeless solution with respect to this kernel. Okay, and the kernel has this ugly form. I think everyone knows this. As m goes to infinity, as the number of neurons in this one-layer neural network converges to infinity, the kernel, sorry, this should be little hm, converges to this kernel. our cosine kernel, if you wish, with this function. And then we show that the theorem that I just stated before with integer powers, with that multiple descent, that actually can be extended to this case, where here you have a slightly more complicated function than just a function of a product. So I think we made very little progress here, but there are some interesting questions kind of in the middle that we played around with, and I think there is a lot of work to be done in that regime. Thank you.
Any questions, comments? Greg?
So I think I just missed part of the talk. I think so where you had the zigzag thing with the multiple descent, is the problem setting? What is the ground truth in the problem setting?
What is the problem setting?
The problem setting is like you have a kernel, and then what is?
Yes. So the assumptions are like that. The kernel is of that form, so it's in a function of inner product, and coordinates are independent. They don't have to be IID, but just for simplicity, independent and identically distributed. Sub-Gaussian. We have a Taylor expansion, and the regression function is representable as a combination of kernels.
I see. So you kind of mentioned this, like the sub-Gaussian thing, like the distribution of the variable should be like approximately on a sphere.
So I mean, it's a high-dimensional thing, so you can do your concentration, right?
Yeah. I don't know. You might be like easier to just
it's actually
to do. Like,
so in this setting, it's not easier to go. I think if you force it to be on a sphere, then you have to take the Hermite polynomials and but in this setting, we don't assume anything about the P except for sub-Gaussianity. I'm not sure it's easier to force it to be on a sphere.
Oh, I don't mean force it. I just mean like in high dimensions, like the sphere, like this concentrates around a sphere.
Sure. Yep.
Okay. Thanks again, Sandra.
Okay, so for the last talk of the morning, we're going to have Andrea Montanari from Stanford, who is going to tell us about the generalization error of random features.
Okay. Thanks for the invitation. Very nice workshop. So as several of the previous speakers, I can leverage economy of scale and do no introduction. but I'll do a couple of slides about my co-authors. This is based on 3 papers with 6 co-authors. The last paper I'll talk about is with Song, is precise asymptotics, blah, blah, blah. Song is there, so go talk to him and ask him difficult questions. The second one is with Song, Beruse, and Theodore, and actually is related to something that, the paper that Sasha mentioned. And the first paper that I'll talk about is with some older people that don't deserve, don't need introduction. Okay, so the motivation for us was, again, this paper and the sequence of paper. In particular, here I referenced this by Misha, Daniel Shu, and Sumit Mandal about the 2 layers phenomenon. But you know everything about this already. And the question is, do we understand these curves? And what does it mean? Do we understand these curves for us? There are a series of interesting phenomena going on here in this curve, and let me tell you what are the 4 most important things that I see. There is this peak at the interpolation threshold, so the fact that when you start interpolating the data, the risk shoots up. This is a little bit of a mystery. There is something that people mentioned before, and is striking, that the minimum is in the overparameterized regime, is in the interpolation regime. So you need to interpolate in this model to get optimal risk. So you have to really put a lot of parameters in your data. On top of that, many of these curves, perhaps this one, but surely others, are monotone decreasing in the overparameterized regime. So not only you need to overparameterize, but you need to overparameterize really a lot, right? So if you put whatever number of parameters, it's better to add parameters to your model. And finally, you're using no regularization, or at least no explicit regularization. There is probably some regularization that is induced by the algorithm, like the mean norm regularization, if it is least square fitting, but you don't put a positive lambda, or don't put a positive explicit regularizer. Okay, so ideally we would like a model that has all of these features, and ideally we would like this model to do real neural networks. So here is what I would like to do if I was good enough. I would take neural networks, say 2 layers neural networks with n neurons. So here I fit parameters AI and WI. I would train stochastic gradient descent until the gradient error gets to 0, compute the test error for this network that I produce, and then be able to compute this in analytic form and display this phenomenon. Okay? This is my dream calculation. I'm not able to do this. Perhaps we'll be able to do it in a few years, but at the moment is too far. So what we can do so far is work with, towards that goal, is work with linearizations of this neural network. And this is also a line of work that has been mentioned before. And the idea is, instead of working with 2 layers neural network, I work with some linear approximation. The simplest linear approximation of a 2 layers neural network is the random feature model. So this was mentioned by Daniel, is simply the model in which I don't fit the first layer weights. I don't fit the WI. The WI are given at random and just fit the AI. Okay? And throughout the talk, the WI, so I will live in D dimension, my data will be in D dimension, and my model will be that I take the WI uniform on the sphere. There is, of course, another linearization that is even more interesting, but more difficult to work with, is the linearization that you obtain when you Taylor expand around W, random W. So this is this neural tangent kernel, and I actually brought only a piece of it here. That is the most challenging piece, is when you expand the WI. So here I fix the W and I fit this parameter AI, but the AI multiplied the X, okay? So this produces some technical complication that makes the model more difficult. Okay, and there is a sequence of papers that show that in certain regime this is not a bad approximation. Okay, so this is the plan of the talk for today. I'll first discuss a very simple Gaussian model for this linearization. And what it can explain. Then I'll discuss the real, basically the 2 linearizations that I mentioned and the approximation question for this linearization. And finally, I'll discuss the generalization question, so the finite data set question. Okay, so here is the Gaussian model. And this is, I'm going fast over it because it's very similar to, very much related to things that have been mentioned before. So again, the setting is that I have n data points and say that I construct features Zi. For instance, the 2 linearizations that I discussed before give me a specific way to construct these features. And then my data are a linear functions of this feature plus an error. Okay, and I do fitting by doing a ridge regression and then taking lambda to 0. That gives me the mean norm solution. And what I'll be studying is the test error, that boils down to this. So the error that you make on any new data set. So you predict with beta hat times z, and you compare it with the true label that is beta 0 times z. Does this setting make sense? Okay. And what I mean by a stylized model, it means that I take my feature Zi to be IID Gaussian with some covariance. Okay? And this, of course, is not very realistic because this phi is nonlinear. So even if your data were Gaussian to start with, they end up not being non-Gaussian. But it's a starting point. Okay, and if you set yourself in this model and you let p and n go to infinity, so p will be the number of parameters and n the number of data points. We let p and n go into infinity and with the ratio converging to some fixed number gamma, you can use random matrix theory to compute the limiting risk. And the simplest case that it's really an exercise is the case in which sigma is the identity, the covariance is an identity. In this case, you obtain a very simple formula, very simple explicit formula that is the following one. For gamma less than 1, you get a curve that diverges as gamma goes to 1. This only depends on tau. So here tau is the variance of my noise. So this goes to 0 with tau. So this is pure variance. And then for gamma bigger than 1, you get two pieces. One piece that is variance, and this decreases with gamma. This piece proportional to tau is what mostly Peter was focusing on. And then you get in this model a bias term that increases with gamma. Okay, so the paper contains results not only for unit covariance, but for general covariance, meaning that the empirical distribution of the eigenvalues converges weakly. So this is the standard setting of random matrix theory, and not only for Gaussian, but for linear transform of a vector with IID entries. So they're more general. In this setting, the formulas are not that explicit, and they are not that explicit because they depend on the distribution of the eigenvalue of this, but there is a general technology to get this formula. And this is, of course, related to these two papers that were presented before. So if you plot this curve, already something interesting happens. So this is the curve that you obtain. I plot versus number of parameters over number of data points. I plot the risk. And this is the interpolation threshold. And this is the p-equivalent threshold. Okay? And this is tree value of the SNR. What is the SNR? The SNR is the ratio of the norm of beta to the size of the noise. So the SNR is R square over tau square. Okay? So as the SNR gets large, you get, interestingly, you get this peak. So you get, of the four features, properties that I described before, you get two of them. You get the peak at the interpolation threshold. Okay, we get, this is for mean norm, so we have vanishing explicit regularization. We get a monotone decreasing curve in the overparameterized regime, so we get also this in these cases. But we don't get the global minimum in the interpolation, in the overparameterizing regime. Okay? So the global minimum is the underparameterized regime. Okay? There is another more fundamental thing that is not satisfying about this model, is that this model, the way I set it up, it ties completely the dimension with a number of parameters. So the feature vector xi live in d dimension or p dimension, and I use exactly p number of parameters. So the two are tied together, which is not appealing. One way to go beyond that is to study a misspecified model. I will not describe it much before here, but basically yi you have in reality, say, zi and z tilde I features that are jointly Gaussian, but you fit only using the zi. Okay, so use only the zi, not z tilde I, and so the model is misspecified. And now if you play with this model, you can get global minima in the overparameterized regime. So if the model is misspecified, what happens is that the curve, you get the peak here, monotone decreasing here, or monotone decreasing and then increasing, but you can get a global minimum here. For instance, this is the green curve. Okay? So this is so far as you can get with this simple Gaussian model, and you can probably play with your sigma and your misspecification ratio and get a sort of, all sorts of geology of this curve and move the global minimum much to the right, even infinitely far on the right. But, as you see, the model is a little bit too flexible in a way. It contains a lot of freedom. You can specify the degree of misspecification and whole covariance. Okay, so the next thing I want to do is go towards a more, say, a realistic model or a more concrete model, and the setting will be the one on nonparametric regression. So I assume that I have IID data, and the data are uniform. The feature vectors are uniform on the sphere. For technical reason, the sphere has radius square root of d, but that's not important. And then the labels are just some base function, some ground truth function, f star of xi, plus noise, and the noise is Gaussian, which means 0 invariance to I. So this is exactly the model that Sasha was mentioning, except that the data are uniform on the sphere, or you can think of them as IID Gaussian. Okay, so we have this random feature model that I described before. Is the model in which I fit only the second layer weights. And the way I fit the second layer weights, I'll do ridge regression again. So I minimize over di, the empirical risk plus a ridge penalty. So one way to think about it is, of course, that this is approximating a kernel. It's a low-rank approximation of a kernel method. Okay, and I'm interested in the test error. That is what I described before. And my first question is, okay, what can I fit if in the population limit when I have infinitely many data? Here I will have 3 parameters, right? I have n, that is the number of data points. So this is the data size. Capital N, that is the number of neurons. And d, that is the dimension. Okay. So the first question is, what happens if the data is infinite in the population limit? This is a little simulation in which I take this random feature model and I take a function that I'll describe in a minute, and I fit random feature models with increasing number of neurons, 40, 80, 120, 160, in 20 dimensions, plot the test error, and I compare test error with R naught. R naught is the test error of the trivial predictor, the predictor that predicts everywhere 0. Okay? So as you see this curve, if you follow one data set, for instance, I don't know, the red, it spikes, it goes down. This is the double descent curve. Here we are interested that small n go to infinity, so I'm interested in here seeing what is the asymptote when you have a lot of data. And you see that the asymptote is not too good, right? With 40 neurons, I do no better than the trivial predictor. With 160, I do a little bit better. And if the dimension increases, things go worse and worse. If the dimension is 100, even with 800 neurons, I cannot do better than the trivial predictor. So this was my first encounter with these random feature models, and I was like, okay, this is not really a very clever method. Now you might ask, of course, okay, so the conclusion, random feature is no better than trivial predictor. You might ask, is this because your target function is very difficult? And this is the target function that I was trying to Okay, it's not very difficult in my work, but it's a second-order polynomial. Or perhaps it's very, very difficult for other people. No, second-order polynomial. So random feature model seems to be unable to fit second-order polynomial on high-dimensional spheres. Okay, interesting. Okay, can we prove this? Yes, we can prove that. So the theorem goes like this. Take any integer L and assume that the number of neurons is less than d to the L plus 1. Okay? So if the dimension is 100, probably you cannot dream of L bigger than, I don't know, 3, 5, 3, 4, or something like that. Right? So fixed integer L, and okay, there is an extra delta positive. Then with that probability, what happens is that the risk of random features is decomposes roughly in 2 parts. One is the risk of random feature on the low degree component of f star. So you can write f star as decompose it into the projection on low degree polynomial and the projection, the orthogonal complement. And the projection is with respect to the uniform measure on the sphere. right, in L2 of the uniform measure in the sphere. And here I'm saying is that the low degree component random feature does something, but on the high degree component, it doesn't do anything, right? Yeah. So this in particular is a lower bound. So for example, to come back to my previous model, so this is, in other words, this is the risk that I would obtain by fitting degree L polynomials, by doing least square fit, and the population will reflect degree L polynomial. So this is saying, for instance, is that if the number of neurons is less than this square, then random feature regression doesn't do better than linear regression. And this is what was happening in my example before. If you think of my example before, this has zero projection on linear functions. So here, a linear predictor does very bad, and a random feature is doing very bad. Okay. Of course, there are all sorts of results about random feature regression. In particular, there is a very nice paper by Francis Bach doing this, but strange enough, it was never studied in this kind of n and d growing together asymptotics. And okay, here I mentioned the results for random feature. We can prove the same result for neural tangent kernel. The only thing that you can changes is that it's not number of neurons that matters, but the number of parameters, which is number of neurons times dimension. In the neural tangent kernel, the number of parameters is n times d. So now neural tangent doesn't look any better than random feature from the approximation question. So the picture that you get from this is the following. So what we get is really a lower bound, but we can actually prove also an upper bound for random feature is that as n increases, so I plot here log n over, this is a cartoon that I did just like, log n over log d is the exponent. So log n over log d equal 1 means that n is proportional to d, n proportional to d square, n proportional to d cube, etc. At each of these thresholds, the risk goes down, and these levels are basically the residual or the error of projecting on low degree polynomial, or is the high degree component of this. Okay. By a simple mapping, we can obtain, just a comment, we can obtain a similar result for kernel regression, but where now capital N is replaced by the number of points. So I think this staircase picture is basically very much related to the zigzag picture in Sasha's talk.
But this is in population?
Yeah, but okay, I can explain the mapping, but you can switch capital. So we have here is, so this is at n finite, n infinity, and n finite. Okay, your setting is n infinity because it's the kernel, but n finite. It turns out that these two plays exactly the same role. So sigma plays the role of k, and you can switch the two, at least in this model. So we have as a corollary of this in the paper, we give a similar result where this is log lowercase n, and is a lower bound. Okay, so this leaves open, of course, the question of what happens at finite n. And so we would like to now understand the full generalization curve. The model is the same as in the last part, but now I'll take the three n and d going to infinity and proportional. And the two ratio will be psi1 and psi2, and this choice is just to confuse you. So psi1 is basically number of neurons over number of dimensions, and psi2 is number of data points. And I'll stick to this ground truth function. We have some results about more general function, but basically this is the difficult part. If you think of the previous, in this regime, you cannot fit quadratic function or higher order function, so you can only hope to fit this. Higher order terms behave as noise. Okay, this is a theorem. I didn't write the authors, but this is again with Song. Okay, you define a couple of parameters that depends on the activation function. And then the theorem looks like this. that for any lambda equal to 0, the risk of random feature is equal to something plus small of term, and this something depends on zeta, this parameter that depends on sigma, psi1, psi2, the regularization, and decomposes into a bias term that is proportional to the norm of beta 0 and the variance term, and depends on the two functional calligraphic B and calligraphic V. And when I use calligraphic, typically for me means that this is quite complicated. but these are explicitly given. Okay, they are explicitly given. I mean, so okay, it's a bit, with a given font, it fits in a slide with a suitable font fits in. But okay, if you look at it, this is really solving two, degree 4 equation to find in this and substituting this formula in three polynomials, and then you get this. So it's something that you have. The most difficult thing you have to do is solve the 4th degree equation that in 2019 we can do. Okay, so if you don't like to parse that formula, this is what we are really doing. The math that is behind this is random matrix theory for kernel inner product random matrices, and is something for which technology exists. And if you know about random matrix theory, you recognize that these are typical formulas that appear in random matrix theory. These are Stieltjes transform, and this is fixed point equation for Stieltjes transforms. Okay, so you can plot them. They are degree 4th equation. You can solve them. You can plot them. And here what it looks. This is for lambda 0 plus. So this is the ridgeless limit. And now you have divergence at the interpolation threshold, global minimum in the overparameterized regime, and monotone decreasing in the overparameterized regime. And actually, the global minimum, so it's in the extreme overparameterization. So this is the curve that appears, that is empirical in the paper of Daniel. And so they plotted, simulations point like this. Now we can compute a curve. Okay, what insights can we get from this formula? Okay, so I'll mention 3 insights, 3 or 4 insights. We always get this singularity at the interpolation threshold, and the minimum is in the extreme overparameterized regime. So this is plotted versus number of parameters or number of neurons over dimension. So we always get this curve goes up and then goes down, and then goes up and goes down. Both variance and the bias are singular. So this is different from the simple linear regression model that we and they analyzed. In that model, this divergence here is a purely variance phenomenon. So there is this variance bias decomposition, the divergence is just variance. Here we plot the bias and the variance, and both diverge. So in particular, the curve has basically the same shape even at 0 noise. The same phenomenon appears at lambda positive. So here what I do is that I plot as a function for various values of lambda, and here is as a function of the interpolation ratio, the overparameterization ratio, capital N over lowercase n. So you see the lambda equals 0, the ridgeless case is the dashed curve, and this is from the yellow to the dark blue. These are decreasing value of lambda. So when lambda is very large, you don't see peak, but then the peak starts developing. But nevertheless, at any fixed lambda, you get that it's better to go to extreme overparameterization. And this is an interesting phenomenon, is that, you see, so here I plot 2 curves for, one curve for low SNR and a curve for high SNR. And then I plot it now as a function of lambda for various value of the ratio psi1 over psi2, which is capital N over N. Okay? So it always, you see, first of all, as the ratio psi1 over psi2 changes, the various curves have a lower envelope. And the lower envelope is where you want to sit, where you want to work. This lower envelope happened to be at psi1 over psi2 infinity, so in the extreme over-parameterization regime. But now the behavior is qualitatively different at high SNR at the low SNR. As a plot as a function of lambda, at low SNR, the minimum is achieved at some positive lambda. It means that at low SNR, what you should do is over-parameterize a lot, but then put a little bit of regularization. Okay? So you shouldn't interpolate. You should over-parameterize because this makes somehow your model rich, but then you should regularize. But so this is kind of the traditional, a more traditional philosophy. This is something that is more surprising, or it's the more phenomenon that you see in neural networks, I would argue, is that, you should over-parameterize to make your model richer, but then you should not regularize. So the minimum is achieved and there exists a critical value of the SNR such that above that critical value, this is what happens. And this is something that I like because, you can imagine that data set in which, modern neural networks or large model works well are high SNR data sets, and so you see this happening. Okay, as a conclusion, I think, so far I understand two mechanisms. So there is this phenomenon of parameterization that avoids poor generalization, and so two mechanisms for this happening. One is this early stopping regime that I spent some time working on, and another one is this high-dimensional interpolation regime that I don't really yet understand, but I think we are understanding more and more. And there are a bunch of questions. Of course, what happens with fully trained networks? And really, I think from a practical perspective, the most interesting question is this one: when is extreme over-parameterization and interpolation optimal? So when is that I can go to a practitioner and tells him, what you're doing is right, or no, you should regularize your network? And as far as I can tell, this is one case. This random feature case is one case in which I can compute a value of the SNR and tell, above this SNR, you should go that way. Below, you should regularize. Thanks. That's all.
Your plots were for what activation of the non-linearity? Like for what?
So the activation in the plots, the activation is ReLU. But if you look at if you carefully look at the formula, now if you look at the theorem, this depends on sigma only through these two parameters, B1 and B star. And what are B1 and B star? B1. I didn't write it here. So, so B1 is the projection of sigma onto linear function in the space, in the Gaussian space, and B star is the projection onto nonlinear function, so second order and more function in L2 of Gaussian. The fact that it's everything in L2 of Gaussian is because we are taking data on the sphere. If you took data IID like Sasha is doing, probably will be L2 of the right measure.
So would the interpolating threshold still be 1 for other activations, or this is very...
Well, this is linear model, so it's 1. Yeah, so you have to go to nonlinear models to get it different. You can do that. Yeah.
So this like multiple descent behavior, this depth-wise behavior, is to a large factor a result of the fact that you're on a uniform sphere or like isotropic Gaussian or something, where the eigenvalues have degeneracy, or like you have like large eigenspace, large neutral eigenspace where the eigenvalues are the same.
This thing is related to the fact that there is symmetry, right?
Right.
So this fact is really related to, you hit. There is degeneracy in the eigenspaces of a given degree, and then you hit the space and you start fitting. But still, I mean, before doing it's kind of surprising it because, here, for instance, you still have a number of parameter that is d to the 1.99. A priori, it's non-clear that you wouldn't have decreased a little bit there, right? So it's clear that,
So
It's what
if
I-
you like, so in realistic data.
But let me add something. So, but this is not limited on a sphere, because if you do, for instance, IID data, you will have invariance under permutation, and then you have the same degeneracy because of that.
Exactly. Yeah, exactly. But like if you look at like the eigenvalue distribution of like CFAR, it really doesn't look like a step. It's just like a naturally decaying distribution.
Sure.
So do you feel like there's like what is a sensible setting to study that kind of?
Well, okay. I mean, what I like about this is that this model, uniform on the sphere or other similar models, that it decouples a little bit the question of learning the distribution of x from learning the function f, right? And I think that the most difficult part of this whole business is learning the function f. Now, or figuring out low-dimensional structures in the function f. Now, we have something that we worked a bit on is the following: what happens if you try to extend to this result to elliptical, basically to something that doesn't lie on a sphere but lies on an ellipsoid. And something that comes out is that you have similar D, but a similar phenomenon, but now there is an effective dimension that depends on. It's not the ambient dimension, of course, and it's not the reduced. It depends on the thing. So we are okay. I cannot go in more detail now, but it's some kind of elliptical data.
Okay. Thank you again, Andrea.